I did the treasure hunt, a beetle's shell that flashed green from one angle and gold from another, and my grandmother's opal, whose fire slid from green to orange as I tilted it on the windowsill, a band gap out in the open air, a zone edge doing its work with no electron anywhere in the story. But George, I kept snagging on something. Every treasure on that list is a sheet or a block, layered scales, spheres packed in every direction. And everything this series has ever built lives on a line. One row of atoms, one twist axis, a waterline that's a pair of points. You signed off promising we'd finally leave the one-lane road, that the waterline would grow into a shape, that a honeycomb would make electrons forget their mass. So, what does a band even look like when the crystal is a grid?
It looks like country you can hike, and that image carries the whole day, so here's the itinerary. First, we build the simplest flat crystal there is, atoms on a checkerboard, and watch the band stop being a curve and become a landscape. Then we pour in the sea, and the waterline stops being a pair of points and becomes a shape. Then the star of the day, the honeycomb, where the diatomic trick gets drawn flat and the two bands touch in a way no chain can imitate. Electrons that behave as if they're massless, living in pencil lead. Then a sobering finale, we let the lattice be dirty and find out why the one-lane road we've lived on all series was the most fragile place to build a home.
Then start the hike. When I try to leave the line, I picture graph paper, an atom at every crossing of streets and avenues. Is that the right first crystal? And tell me what survives from the chain. Each atom still an identical well, still one little amplitude arrow per atom, hops still leaking between neighbours.
All of it survives. The only new ingredient is geometry. Atoms at every crossing of a square grid, identical wells, the same spacing at east-west as north-south. Every atom now has 4 nearest neighbours, east, west, north, south, and the same hopping amplitude T for leaking to each. The electron's state is what it's been since the first episode, a complex arrow at every atom, length squared giving the probability. What's new is that a step now comes with a choice of direction, and that choice reshapes everything downstream.
Then the twist has to change first. On the chain, a state of definite energy meant one fixed twist per step, a single number K. But a step is ambiguous now. I can step east or step north, and nothing says the arrow twists the same amount for each. So the twist becomes a pair, a rhythm along X and a separate rhythm along Y, which makes K an arrow, a thing with its own direction.
An arrow is exactly right, the most consequential upgrade today. Call the east-west rhythm Kx. The arrow advances by Kx times A with every step east, and the north-south rhythm Ky, advancing by Ky times A per step north. Together they make a vector, a magnitude for how tightly the wave is wound, a direction for which way the crests march. And block survives untouched. Last episode, we saw the theorem never cared what was waving, and it cares just as little how many directions the repetition runs. The wardrobe fits a sheet as well as a line, with one twist dial per axis of repeat. The redundancy runs per axis too, so the zone stops being an interval. It's a square patch of twists with 4 corners.
Then I want to guess the energy from the picture. Stand on one atom. Its east and west neighbours don't know how the arrow twists northward. Those hops feel only the east-west rhythm. The north-south pair feels only Ky. 2 directions, each one looking just like the chain we already solved. So I'd bet the band is the first episode's cosine, once per axis. The 2 contributions simply added.
Let's put the bet through the machinery. Stand on the atom at some crossing and ask who lands there. The eigenvalue equation. 4 neighbours reach in. The east neighbour's amplitude is your own arrow advanced by 1 eastward twist. E to the I kxa, the east twist per step, times yours, and the west neighbours is one twist backward, e to the minus I kxa, each arriving with its hop, minus t. Add the pair the way Euler taught us. One unit arrow tilted up by kxa, one tilted down, imaginary parts cancelling, and you're left with minus t times 2 cosine of kxa. The north-south pair runs the identical argument with the other rhythm and gives minus t times 2 cosine of kya. And the crossing's own address cancels out of every term. The old test, passed again, that the twisting guess really is a state of definite energy. What remains, said slowly, E of k equals the on-site rent, minus 2t times the cosine of kxa, minus 2t times the cosine of kya. Your bet pays out. The first episode's cosine, once per axis, added.
What I need to absorb is what kind of object that is. On the chain, E of k was a curve, energy against one twist, drawable on a napkin. This is a number sitting over every point of a square patch, energy against two twists at once. That's not a curve, that's a surface over an area. How do you even draw such a thing?
The way hikers draw mountains, as a topographic map. Let the square zone be the ground, the energy at each twist, the altitude, and hike it. At the center of the zone, no twist at all, every arrow aligned, the energy is pulled down as hard as it can go. The deepest point on the map, a valley floor, deeper below the rent than the chain's floor ever reached, both cosines pulling at once. At the four corners of the zone, both rhythms fully staggered, every arrow fighting all four neighbors, both cosines push up. Peaks, the roof of the band, the same fully staggered state, printed at each corner of the map. But there's a third kind of landmark, at the midpoints of the zone's edges. Walk to one and tell me what's under your feet.
Midpoint of the eastern edge. So the east-west rhythm is maxed out, fully staggered, its cosine pushing the energy up as hard as it can. But the north-south rhythm is zero, aligned, its cosine pulling down just as hard. Equal push, equal pull. The terms cancel, and the altitude there is exactly the on-site rent, dead level, halfway between floor and roof. And the ground itself. If I walk along the edge toward a corner, I'm climbing toward a peak. If I turn and walk inward, I'm descending toward the valley. Rising one way, falling the other. That's a saddle, a mountain pass.
A mountain pass at every edge, midpoint, level with the rent, curving up along one direction and down along the other. Now finish the map with contour lines, curves of constant energy, the brown loops on a hiking chart. Around the valley floor, small closed loops ringing the center. Around the peaks, loops ringing the corners. And at the exact altitude of the rent, the contours do what contours always do at a pass. They run straight through it and cross. One map, three landmarks. Floor, peaks, passes. Band structure as terrain. Every question we ask for the rest of the day is a question about this ground.
So the band I'm carrying isn't a curve anymore, it's country. A valley at the center of the twist patch, peaks at its corners, passes standing level with the rent between them. And this show has a reflex the moment it owns a band. Pour in the crowd. I assume exclusion doesn't care that we've changed dimension. Every twist still a bench with two spin seats, no sharing, fill from the bottom up.
Paulie doesn't blink. A state is a state, one electron each, two spins per twist, cheapest seats first. So pour. Electrons settle into the valley and stack upward until they run out at some level. On the chain, that level cut the band at a pair of points. On a map, filling to a level means flooding the terrain. And a flood in a valley makes a lake, a filled region of twists with a boundary where wet meets dry. The waterline of the Fermi Sea is now a closed curve on the map, the shoreline of that lake. And the shoreline is the object last episode named in its final breath, the Fermi surface. In a flat crystal, the Fermi surface of a metal is a shape you can draw.
Then let me draw the first one. Take a nearly empty band, a puddle, not a lake. The puddle hugs the deepest ground, and right at the valley floor, the terrain is a smooth bowl. Any smooth band bottom is locally a parabola, last episode's guarantee. The same parabola whichever way I walk, because both cosines are just beginning the same gentle bend. A round bowl floods in circles. So, the shoreline of a nearly empty band is a small circle around the zone center. And a circle is the free electron smiling back at us, isn't it? The pincer again. Near the bottom, a block electron is a free electron at a retuned mass, and here the exchange rate reads the same in every direction.
Circles it is, the puddle stage of every simple band, where free electron thinking holds and one effective mass tells the whole story. And the circle is already a statement of temperament. Same curvature every direction, same speed every direction, an even-handed metal. Now keep pouring, because the interesting question is the landmark filling. 1 electron per atom, the sodium count, makes the band exactly half full. What shape is the shoreline then?
I'll back the bowl. The circles have been growing outward from the floor, and nothing I've heard tells them to stop being circles. So half filling should just be the biggest circle so far, a round lake sitting halfway up the valley. I'll commit to that.
And there the terrain overrules you. The bowl is only the floor, and by half filling the lake has long since left it. Where does the water level sit? Use the map's symmetry. For every twist below the rent, there's a partner above it. Pair each twist with the one as far short of full stagger as it sits past none, and each cosine flips its sign. So seats below the rent and seats above it match 1 for 1. Exactly half the band lies below. Half filling parks the water level precisely at the rent, and you've already stood at the places whose altitude is exactly the rent.
The passes. At half filling, the water has risen level with the 4 passes, so the shoreline can't be a circle. It has to pass through those 4 special points. What does it look like in between them?
Dead straight. The shoreline at the rent is the set of twists where the east-west cosine exactly cancels the north-south one. Whatever energy a step along x adds, a matched step along y removes. 2 angles that add up to half a turn have equal and opposite cosines. One hand as far past noon as the other is before it. So the balance holds exactly when the 2 twists sum to one fixed total, kx plus ky pinned, and a fixed sum of the 2 map coordinates is a straight line from one pass to the next. 4 passes, 4 straight banks. The half-filled shoreline is a perfect square, rotated to stand on its corner inside the square zone. On the chain, half-filling was a pair of dots. Here it's a geometry nothing on a line could have predicted.
A square lake standing on its corner, drawn inside a square zone tilted the other way. Now cash the big claim, because last episode's sign-off said the geometry of this shape becomes the entire personality of a metal. And personality is a lot to hang on a shoreline.
It's the right word. Everything a metal does, it does at the waterline. The deep sea is as silent on a sheet as it was on the chain. So the metal's temperament is the shorelines. A waterline electron's speed is the steepness where it stands. Its direction points across the waterline, wet toward dry. So which directions carry current fast is written bank by bank. For our even-handed checkerboard, the 4 banks balance overall. The shape shows itself when you probe the sea bank by bank, which is what the fingerprinting measurements on copper do. A circular shoreline answers a push the same way from every side. The corner standing square is another animal. A whole stretch of bank marches in lockstep in one shared direction. Push the sea with a field and the whole lake shifts across the map. The response is the lake's shape through and through. and 1 breath for the block. There the shoreline becomes a sculpted closed surface. Copper's is nearly a sphere, with necks reaching out to grab the zone boundary.
Here's what I can now see that I couldn't an hour ago. The band is country, the metal is a lake in it, and the metal's character is its shoreline. Which raises the ledger question. The Fermi Sea episode built the seat count, the density of states, seats per stretch of energy, 1 over the slope, and on the chain, the flat band edges hoarded seats. The pile-up grew without limit at the bottom and top of the band. Up here, the flattest stretches are around the passes, so I'd expect the crowding to move there. But what happens at the band edges now? Does the blow-up survive the extra dimension?
Flood and count. Seats spread evenly over the map's area, 1 comb tooth per patch of twist ground, so seats per stretch of energy is just the new area the water claims per small rise. Start at the valley floor. Each rise claims a ring of fresh ground. Near the floor, the ring is short around but wide across, because the ground is nearly level. Higher up, it's long around but narrow, because the walls have steepened. The two effects trade off, and the flooding claims area at an almost perfectly steady rate from the first drop. So in a 2-dimensional crystal, a band edge arrives as a clean step. The chain's edge blow-up was a 1-lane artifact, all those band edge seats crushed into a sliver of energy with no sideways room to spread them out. But when the water level reaches the rent, it isn't climbing a wall anymore. It's creeping across the nearly level ground of 4 passes at once, and 1 tiny rise claims a huge sweep of new area. The flooding stalls, and seats pile up at the pass altitude. The pile-up didn't die in 2 dimensions. It moved from the band edge to the saddle, right where you posted it.
Steps at the edges, a crowd at the passes, ledger closed. Now the star. Last episode's promise was specific. Carbon atoms arranged in a honeycomb, 2 interleaved sub-lattices, the diatomic trick drawn flat, and electrons near a touching point behaving as if they have no mass at all, riding in every pencil line I've ever drawn. Build me the honeycomb because I already smell the trap. Chicken wire is not graph paper.
It is chicken wire. A tiling of hexagonal rings, every atom carbon, every atom bonded to exactly 3 neighbors instead of the checkerboard's 4. And the trap is the key structural fact. The honeycomb is not a simple grid. On the checkerboard, every atom saw an identical world. 1 atom per repeating cell did the job. On the honeycomb, look at 2 bonded atoms. One sees its trio of neighbors splayed like the letter Y, and the other sees the same trio upside down. No slide of the whole pattern can turn a Y over. So the honeycomb is 2 interleaved triangular sublattices, A and B, threaded through each other, with a repeating cell holding 1A and 1B. You know this cast. It's the diatomic chains, drawn flat, with 1 loaded difference.
And I can name the difference. 2 atoms per cell means 2 amplitudes, alpha on A, beta on B. Bloch collapses the whole sheet into a 2x2 puzzle at every twist. 2 solutions per twist means 2 bands, except bands are terrain now, so 2 sheets of terrain, a bonding sheet below, an anti-bonding sheet above. And on the chain, the gap at the crease equaled the difference in well depth. That was the knob. But here both atoms are carbon, identical wells. The knob sits at 0, so nothing can hold the crease open. Somewhere the 2 sheets have to touch.
They have to touch. And where is the prettiest geometry in the subject? With the well depth knob at 0, the only thing separating the sheets at any twist is the coupling between the sub-lattices, the connector in the 2x2. Remember what the connector is made of. The hop routes from an atom to its partners on the other sub-lattice, each route 1 unit arrow whose angle the twist sets, adding like clock hands, and with identical wells on the diagonal, the sheets split symmetrically by the connector's total length. Wherever the connector has length, the sheets are pried apart. Wherever its arrows cancel to nothing, if anywhere, the sheets meet. On the chain, there were 2 roots, 2 arrows. Here, every A atom talks to 3 B neighbors, 3 roots, 3 hop arrows on the dial. So the whole fate of graphene turns on one question. Can 3 unit arrows add up to exactly 0?
2 arrows cancel only when they're back to back. That was the chain's zone edge. 3 unit arrows. I can see it on the clock face. They cancel when they're spread perfectly evenly around the dial, each a third of a full turn from the next, a 3-pointed star. Lay the 3 head to tail, and they close a perfect triangle, ending where they began, sum 0. Tilt one and the triangle can't close, a leftover pokes out. So the sheets touch wherever the twist arranges the 3 hop arrows into that star. Does any twist actually manage it?
Exactly 2 do, and the counting tells you why so few. As you dial the twist around the zone, the 3 arrows turn at different rates because the 3 neighbor roots point in different directions, each arrow's angle growing with the twist along its own route.
Hold on, before you count, is the map still a square patch? The honeycomb doesn't repeat on a checkerboard.
Good catch. It repeats on a triangular pattern, and its patch of twists comes out hexagonal. 6 corners now, not 4. Keep that map in view while we count. Demanding the perfect star is demanding 2 coincidences at once. The second arrow, a third of a turn past the first, and the third, another third past that. 2 conditions, against 2 dials to tune, kx and ky, so solutions come as isolated points, not curves, and the lattice's symmetry places them at corners of the zone. The hexagon's corners look plural, but the zone's wraparound files most of them together. Only 2 are genuinely different places. At those 2 points, and nowhere else in the entire zone, the star closes, the connector dies, and the 2 sheets touch.
So say the object whole, 2 sheets of terrain spanning a hexagonal patch of twists, pried apart nearly everywhere by that 3-arrow connector, and meeting at 2 pinpricks. Now zoom in on a pinprick. What does the meeting look like up close?
Like nothing this series has met. Every landmark so far has been smooth. Flaws and peaks that flatten as you approach, passes that level off. Zoom toward a touching point and the sheets refuse to flatten. The lower sheet rises to the meeting as a cone, straight-sided, sharpening to a true point, and the upper sheet descends as its mirror image. 2 cones, tip to tip, an hourglass pinched to a single point of contact. And read the dispersion of the shape. Near the tip, the energy grows in direct proportion to your distance from the touching point. The same rate east, north, or anywhere in between. Linear and alike in every direction. No bowl, no dome. Straight walls, all the way into the point.
Then the motion toolkit goes haywire, and let me break it in order. Speed is the slope of the band, and a cone's slope is the same everywhere on it, near the tip, far from it, whatever the direction. So every electron in the neighborhood moves at the same speed, regardless of its energy. Feed one more energy and it won't go a hair faster. And mass is curvature. 1 over the effective mass reads off how the slope changes. On a cone, the slope never changes. The curvature dial reads 0, and the formula hands me 1 over 0. What am I supposed to do with that?
You retire it. The effective mass was an idea built for parabolas. Last episode said it flat out. Any smooth band bottom is locally a parabola, and the curvature is the exchange rate that lets you treat a block electron as a free one. The cone's tip is the loophole. It isn't smooth, there's no parabola near it, and the concept retires. And the formula's reading isn't wrong. It says no amount of push changes this electron's speed, which is the same verdict it handed at the old band's inflection point. The new thing is that here a whole neighborhood lives that way, at one shared, fixed speed. And a particle whose speed no energy can change is exactly what massless means. Light is the standard example. That shared speed is the only number of the day. The cone's slope, about 1/300th of the speed of light. More energy doesn't mean faster, only farther from the tip. No slow electrons here, no fast ones, only directions. Two cautions though. These electrons are not photons, and their speed is not the speed of light. It's the slope of this particular band, set by carbon's hopping strength and the honeycomb spacing.
Electrons with no mass to their name, doing a fixed fraction of light speed inside a crystal. Does the meeting point where all of this happens have a name? It's earned one.
One of the best names in physics. The touching points are called Dirac points, the same Dirac whose equation predicted antimatter, because two cones tip to tip is precisely that equation's geometry, alive in a flake of pencil lead. The wave equation of relativistic particles playing itself out on chicken wire made of carbon.
But everything hangs on whether the C reaches the tips. So let me run the count. Carbon donates exactly one roaming electron per atom. 3 of its 4 outer electrons are locked into the bonds to its 3 neighbours. The 4th roams. 2 atoms per cell, so 2 electrons per cell. And the lower sheet holds exactly 2 per cell. 1 bench per twist, 2 spin seats each. The bonding sheet fills to the brim. On the diatomic chain, that same count was the Bourne insulator, full floor, gap overhead, dead shoreline. But here the gap overhead is 0, at 2 points. So the waterline parks precisely at the tips?
Precisely at the tips. And nobody tuned anything. Not near them, at them. Half-filling floods the lower sheet, wall to wall, and the flood stops at the exact altitude where the sheets kiss, because the touching points are the lower sheet's ceiling and the upper sheet's floor. So graphene's Fermi surface, the shape we've spent all this hiking learning to read, is 2 points. The lake has swallowed the whole lower terrain. That makes graphene neither of the things this series knows how to be. Not a metal's life is a long shoreline of ready seats, and here the flooding rate dwindles to nothing at the tips. The last dry ground is a shrinking ring around each tip. Tiny around, steep-walled, so each rise buys almost no new area. A nearly empty ledger. Not an insulator. An insulator's silence is a gap the push can't pay, and here there's no gap at all. Empty seats sit a whisper above the full ones, straight across the tip. It's a third thing, a semimetal, balanced on the knife's edge between the categories and held there by symmetry. The knob is pinned at 0 because carbon is carbon.
A crystal balanced on the exact edge between the only 2 endings this series has ever written. That sounds like a whiteboard limit, not a material. Someone actually holds this in their hands?
Someone peeled it off a pencil smear. Graphite, pencil lead, is a loose stack of these honeycomb sheets, shedding layers onto the page as you write. Physicists in Manchester took a piece and ran the least glamorous procedure imaginable. Press sticky tape onto graphite, peel it away, and a thinner flake comes off with it. Fold the tape, peel again, thinner still. Again and again, until what clung to the tape was a flake 1 atom thick. A single honeycomb sheet, the thinnest material ever made. And when they wired such flakes up, the physics answered as drawn. The cones, the fixed speed, the retired mass, the semi-metal on its knife's edge. Out of the same grey stuff your handwriting is made of.
So the flat world paid out everything the teaser promised. A shoreline with a shape, then a crystal whose entire shoreline is 2 points. Which leaves the sobering finale from your itinerary, and I think I know the door it enters through. There's a line from the motion episode that's been quietly load-bearing ever since. A real electron never finishes its journey. It's constantly getting scattered, bumping off vibrations of the lattice, off impurities, off defects. The vibrations got a whole episode, phonons breeding in warmth, taxing the drift. The impurities and defects never got theirs. Today,
the impurities take center stage, and they play a darker role. Draw the contrast in one line. A phonon merely scatters the electron, resets its twist, taxes the drift, a tax that fades as the phonons starve in the cold. But an impurity is frozen into the lattice, no refrigerator removes it, and a random scatter of frozen floors doesn't just tax a wave. We're about to see it can trap the wave outright. Set the stage. A real crystal is never blocks perfect repetition. A wrong atom here, a vacancy there, sprinkled at random and fixed for good. And the traveller is the motion episodes. A localized electron is a wave packet, a bundle of nearby twists gliding at the group velocity. Send the bundle down a disordered chain, and every flaw it meets throws back a reflected ripple, an echo in last episode's language. Everything hinges on what the echoes do to one another.
And I'd have sworn last episode already answered that. The echoes of a perfect lattice only conspired at special wavelengths because their birthplaces marched in strict rhythm. Impurities sit at random spots, random birthplaces, random lags. So my instinct says arrows pointing every which way mostly cancel. A small leftover survives, and that leftover is the drizzle. Some scattering, a shorter drift, a bit of resistance you live with. The wave stumbles, but it keeps going.
On a sheet and in a block, that instinct mostly survives. On a line, it collapses. One of the deepest surprises in the subject. Your random arrow sum treats each echo once. One bounce per floor, add them up. But echoes get echoed. A ripple bounces off one impurity, the reflection off another, that one off a third. Now ask, what's the total amplitude for the wave to end up back where it started? Among the winding return routes, everyone has a partner. The same route walked in reverse. Same floors visited, same stretches travelled, backwards. A route and its reversal collect exactly the same total twist, so their two arrows always agree. For every other destination, the arrows mill around and mostly cancel. For the return trip alone, they systematically reinforce. Only round trips have this. Reverse a route to anywhere else, and it no longer ends where you asked. Interference loads the dice toward going back.
So the floors don't just trip the electron. Its own echoes gang up and herd it home. And no amount of randomness can wash that out, because the bias rides on paths paired with their own reversals. And on a chain that has to be as bad as it can possibly get, there is no sideways. Every echo retraces the one lane it came down, back through the same floors along the same path. The return routes have nowhere to spread out and dilute.
Nowhere at all. So the effect compounds without mercy. On a line, every scattered ripple retraces its own path exactly. Every return pair reinforces, and each extra flaw multiplies the pile-up. The wave lives in a hall of mirrors where every reflection comes straight back to sender. In one dimension, any disorder, however weak, however sparse, eventually traps every wave in the band. Not slows, traps. Given length enough, every state on a dirty chain becomes a bundle parked around some stretch of lattice, its amplitude dying away to either side, sealed inside an echo chamber built of its own reflections. And mark what kind of silence this is, because it isn't a gap. The seats still exist, at every energy the band ever offered. They've simply stopped travelling. A gap says the crystal has no wave to sell you. Disorder on a chain sells you the wave, pre-trapped.
Which lands the confession late and hard. The one-lane road. The home this whole series was built on was always the most fragile place to live. A perfect chain gave us gorgeous bands, and a pinch of real-world dirt, given length enough, quietly takes the current away. So escaping one dimension wasn't tourism, it was survival. Tell me the sheet and the block do better.
They do in two different ways. On a sheet, an echo has sideways room. Return routes wander wide around the floors, and the homeward bias thins with distance, but so slowly that it never quite loses. Two dimensions is this story's knife edge. The waves barely fail to escape. Given a big enough sheet, disorder still wins in the end, but only just, and a good sheet behaves like a fine conductor at any size you'd ever build. In a block, the escape is real. 3 dimensions holds a genuine threshold. Keep the disorder weak and the sea stays mobile. With a dividing line in energy, the mobility edge, between the states that escape and the stragglers near the band edges that don't. Push past a critical roughness and the sea freezes solid, every wave trapped. The phenomenon is called Anderson localization, and the scope, the picture, a wave trapped in an echo chamber of its own making, is the heart of it. The careful theory is deep, and it took decades to build.
Then let me walk the trail back, because it started on a windowsill and ended in a hall of mirrors. We left the line, the twist grew a direction, and a band became terrain. A valley, corner peaks, passes level with the rent. The sea flooded it, and the waterline became a shoreline with a shape. Circles for a puddle, a square standing on its corner at half filling, a metal's whole temperament written along its banks, while the ledger read clean steps at the band edges and a pile-up at the passes. Then carbon drew the diatomic trick flat, 2 sub-lattices of one element, the gap knob pinned at 0, 3 hop arrows closing into a star at 2 corners of the zone, 2 sheets meeting tip to tip, electrons at one fixed speed, mass retired, the sea parked dead on the meeting points. A semimetal lifted off graphite with sticky tape. And then the reckoning. Sprinkle real dirt into any of it, and on a line the echoes always win.
Held whole. And it opens the door we walk through next, because there's a confession bigger than the dirt. In this entire series, no electron has ever truly seen another. The only conversation between electrons in anything we've built has been Pauli's seat bookkeeping. That bench is taken, sit elsewhere. Polite, silent, and free of charge. But electrons carry charge, and charges repel. 2 electrons squeezed onto the same atom shove against each other, hard. Parking on an already occupied site costs extra, a fee, and the fee has a name, you. Every drawing in this series has quietly set that fee to 0. Turn it on, and the proudest rule band theory owns, a half-filled band means a metal, can fail spectacularly. There are crystals whose bands fill exactly halfway. Crystals that every picture we've drawn insists should conduct, and they refuse, flatly, stubbornly. Next time, when electrons collide.
A crystal that every drawing in my head calls a metal, refusing to conduct, that's a proper villain. And I suspect the parking fee will bend more than one rule before it's done. Until then, the homework is the cheapest lab in physics. Take a pencil and drag one line across a page. Look at the grey sheen and know what you just did. You shed a stack of honeycomb sheets, and in the topmost one, 2 sheets of terrain kiss at 2 points, electrons crossing your handwriting at one fixed clip, no mass to their name. You drew a semi-metal. Then come back, because our electrons are done ignoring each other. Next time, they collide. Thanks, everyone.